Good afternoon. You're tuned in to Weltanschauung, broadcasting from deep in the heart of the Petro Metro, aka Houston, Texas. I'm Mike DeLeonardis, bringing you news and analysis of science, technology, and the human condition. So, this is the long overdue follow-up to our very first episode, The Great Acceleration Part 1. But before jumping into Part 2, let's briefly recap Part 1. In short, the Great Acceleration refers to a recent inflection point in Earth's history, heralding in a new epoch known as the Anthropocene. That is, it alludes to a rapid global transition from the last geological epoch to a new one, specifically from the Holocene, or the recent Hole, to the Anthropocene, the Age of Man. The hallmark of the Great Acceleration was the mid-20th century spike in human activity focused on modernizing the world. Exemplified by the intrinsic coupling of infrastructural expansion with technological commodification, this global effort was ignited by post-World War political and economic policies which further amplified what would already be considered impressive rates of extraction and modification of resources. In other words, the post-war redirection of wartime production capacity toward revitalization and new tech for the masses, incentivized by government directives, shifted global economic activity into overdrive, resulting in unprecedented global infrastructural development suburban sprawl, and rampant consumerism. And so, it's this unparalleled acceleration in development and consumerism that's changing the face of the Earth, along with its geologic, hydrologic, and atmospheric chemistry, which in turn is moving the planet beyond the defining characteristics of the Holocene. This is crucial because the Holocene is considered the sweet spot in Earth's history that enabled the rise of civilization, but the proliferation of industrialization and the commensurate rise in our overall energy quotient pushed our blooming global civilization into a cascade of growth, culminating in unprecedented human exploitation of the world's resources equivalent to that of a new global force. Hence, the Great Acceleration signifies the extent that human activity is destabilizing the Holocene's natural feedback cycles. That's why we're seeing more frequent and larger wildfires, longer and more severe droughts, hotter, more acidic and hypoxic oceans, and more frequent and intense mass die-offs. These are but a few examples associated with the cumulative effect of human activity on Earth systems that are now rapidly being pushed out of their Holocene norms, thereby ushering in an entirely new geological epoch that bears our namesake. As such, the title of Anthropocene actually belies a grim epithet for this new epoch, which is currently being ratified and documented into Earth's 4.5 billion-year geologic record by geologists the world over. So although the rise of civilization extends from the advent of agriculture to the present, the repercussions of our extraordinary proliferation became undeniable around the mid-20th century as the after effects of our activities began reverberating throughout the globe. This acute global change unveils the Great Acceleration, which by and large has been driven by a corresponding rise in the combustion of carbon-based fuels, resulting in a surge of global greenhouse gases, which in turn has trapped more heat from the sun. What this all boils down to is that the escalating disruptions rippling through the biosphere is a consequence of an acute perturbation of the carbon cycle. Hence, this ironically eponymous epoch is punctuated by today's chaotic climatic, terrestrial, and oceanic conditions, presaging a relatively hot and barren world inhospitable to the majority of macrosomic life forms, including us, at its point of equilibration sometime in the future. That's the hothouse Earth we're barreling toward. Typical use and cruise, wham bam, thank you ma'am, see you later alligator, parasitic relationship. But the joyride on Easy Street has inevitably detoured down unknown terrain that's a lot more treacherous. In short, we're on a highway to hell. And so it goes. And that's a brief synopsis of the Great Acceleration, Part 1. Kudos to Dr. Will Steffen for elucidating many of the key points on the Anthropocene, for which I'm eternally grateful. Thanks a million, Will. We concluded the first episode with some brief comments on the human condition, so that's where we pick up in an attempt to make sense of the shadow lurking within the human psyche. Thus, we begin Part 2 by laying a backdrop that touches on universal evolution with a mimetic twist on an unabashed Cartesian model for deconstructing the common thread running through our very being, and connect that to the coevolution of our mindset with our technology. So shortly after the Big Bang, this homogeneous, extremely hot, dense, quirky plasma quickly ionized, forming protons, neutrons, electrons, then atoms, next molecules, all the forces in matter, combining, separating, scaling, spanning, and crashing to create clusters, galaxies, stars, planets, and such. smashing, congealing, and exploding, cycling through the eons of time. Amidst the progression of this elemental chaos of atoms and molecules was the spawning of our own world. A hot molten sphere whose outer layers gradually cooled and congealed into a tectonic mishmash of colliding rocky plates, replete, bathed, and sculpted on its outer facade with a generous helping of water, the elixir of life, and all of this wet rocky stuff surrounded by an atmosphere. Behold, the geosphere, our land, sea, and air. In tandem went the successive emergence of complex organic molecules polymerizing, sequestering, and combining into hydrocarbonated masses of protoplasm, giving rise to the first rudimentary cells, thriving in a soup of minerals blasted out from hot vents on the floors of the primeval oceans. Such was our biosphere once upon a time. Their successors being microbial phototrophs, which began producing the metabolic waste that gradually oxygenated the lower atmosphere and rusted the earth. So went the dance of the geosphere and the biosphere upon the face of our world, embraced in a tumultuous spiral, shaping the earth as we know it, evolving in concert through the ages, via upheavals that eventually gave rise to the biosphere's fundamental chemical cycles we know today. Near the tail end of this odyssey, land-dwelling quadrupeds bucking up on their hind limbs, destined to morph into humans, quasi-bipedal, evolving toward liberated forelimbs for grasping and manipulating objects in their environs. A new, highly adaptable body plan ripe for taking advantage of its surroundings, unlike nothing else before. And all of this life, originating from one atom in particular, yes, carbon, notably endowed with 4 potential binding sites, marking its unique spot on the periodic table. The perfect ratio of mass and size, endowing it with just the right amount of agility to bind with itself and other select elements in such a way to create the countless variety of combinations that brought forth life as we know it. Made to order tetradexterity, unequivocally dubbing it the biochemical scaffold of every living entity. These are the events at the molecular level, given the physical constraints laid out in this section of the universe. Scaling up 10 orders of magnitude from the carbon atom, we find a similar depiction of tetradexterity imprinted on mammalian body plans imbued with highly plastic nervous systems, sensing, manipulating, learning, contemplating, and aspiring. Developing into humans sporting newly liberated upper extremities, much more adept at grasping, examining, and willfully altering things in the environment. The coupled ability to communicate with ever greater sophistication facilitated the elaboration of increasingly complex strategies and collaborations amongst ourselves that paved the way for global dominance. And all of this evolution appears to resemble some sort of fractal progression in terms of complexity and acceleration, extending all the way back to the beginning of the universe. So here we are, sensing, moving, contemplating, the latest iteration among our mammalian kin. And there's something quite interesting about this fractal progression of matter emerging out of space and time. And that's symmetry, evident from the simplest molecules to every known living organism. Symmetry sine qua non being the juxtaposition of mirror images. Chirality, sagittally superimposed. So it is with our brains in form and function, from elementary tasks to sophisticated reasoning, our mindset reflecting the binary or dual, mediated by commissures bridging the two sides. Symmetry is the axis of duality. Duality integral to our fundamental perceptions and reasoning. The singular sensation of moving forward within the three-dimensional aggregate of space. Three spatial dimensions perceived in a temporal context, informed by our senses. Hence, we perceive a tertiary space via our binary senses. Stereotactic, touch, sight, stereoscopic, hearing, stereophonic, and the like. Right, left. The two halves defining our body symmetry etched upon a longitudinal axis. All our senses scaled upon a linear range of juxtaposed opposites, assimilated and processed via a sequence of events, from the most basic reflexes to learning and reasoning, concluding in an action or making a point. Our inherently linear perceptions and interpretations intermingled within dynamic surroundings, changing and synchrony with our actions. Another clasping spiral, to and fro, going on and on and on, in a sort of geometric or, again, fractal progression, and it all informs us. So with the passage of time, we evolve. To reach beyond the limits of our extremities, we develop tools, prosthetics that broadened our horizons, reflecting fundamental experiences, thoughts, and desires. Mimicry, yet with separate progressions inherent to their own utility, not totally under our ability to foresee or control. Hence, the offshoot from the technology we sculpt out of our surroundings has always been followed by unintended consequences. This is the legacy of what we do, which is now impressive enough to be a global force in its own right. Whether you call it the anthroposphere or technosphere, it's now on par with the geosphere and biosphere in shaping the face of the earth, and so our own trajectory. From the development of spheres to the advent of digital and wireless technology, all of this born out of our dual nature, ushering in a superposition of outcomes quintessential to universal duality, the ensuing after effects invariably eclipsing the bounds of our insight, and time being compressed with each successive iteration, which is quite salient because when you think about it, this progression appears to be accelerating, each version outstripping the last. But we typically adjust by falling back on reflexive actions or instincts, given any particular milieu, and so we are left in the dust. No evidence of enough forethought beyond the task at hand, because the limbic brain has much more sway over our meager rationale than we care to admit. Most aptly exemplified by the present mimetic tirades couched in tropes, neotropes, and pseudo-virtuous ad hoc social protocols, gutting any chance of rational discourse or collaboration. An escalating cycle of deceit, hyperbole, and uproar, stoking further divisiveness and gridlock, luring us deeper into a balkanized casing of bubble wrap. Ladies and gentlemen, I give you the latest iteration. Mobile technology and social media, which is indeed tearing us apart by bringing us closer together. The ultimate paradox. This is but one example of the shadow side of our prosthetic desires, and so it is. Glancing into the socio-dynamics of the Technosphere, in essence, this latest iteration, by all indications, has outstripped our ability to control it. Causality, wherein lies the shadow, a mirror image of our very being, barely acknowledged in real time, if at all, yet running through the core of every so-called historical moral thesis, from literary dogma to prose poetry and art. So what of us? But to become progressively amnestic to the engineering and utility of previous inventions as we push the envelope forward. accelerating towards uncharted landscapes born out of successive innovation. Molded anew with meager hindsight, we find ourselves unable to go back, and now we stand at the precipice of definitive self-annihilation via our own devices. Whether by nuclear war, climate change, outright societal collapse, or a likely combination thereof. No longer are we merely left with the magical constructs of the apocalypse brought upon us by the wrath of an angry God. This is the real thing, a product of our own doing, reflecting back upon us, yet hidden in plain sight, exposing some sort of innate parietal flaw, rendering us blind to the shadow. The ultimate dilemma, ineptly termed climate change, is merely a symptom of something much larger. Whatever you call it, it's the immediate task at hand, theoretically solvable, but obliges an unprecedented level of global synergy beyond that amassed during either World War or nuclear detente. Valid remedies conspicuously paramount to our continued existence being eclipsed and stifled under an ever rapidly growing cascade of deceit, distractions, polarization, and half-ass conciliatory measures. And yet, if we actually muster the undivided attention needed to avoid crashing into the abyss hewed by this impending crisis, what then? For any hindsight gained will never be a proxy for the foresight necessary to sustain any truly progressive civilization. Shadows of the things that were, and shadows of the things that might be. And so it goes. And that's a wrap. For what it's worth, the Gedanken musings, referencing a cumulative iteration of nested sets of events from the beginning of time to the present, bubbling out from this rostral sphincter to your ears. In short, food for thought, if you get my drift. Moving on, here's what's on tap. Up next, carbon energy and computing will be consecrated to their own segments, comprised of article summaries beginning with carbon evolution up to and through us, including a brief rundown of a few examples of what climate change is doing and dogmatic responses touted by the so-called intelligentsia. Following that will be a section devoted to exploring research and innovations in carbon-free energy with brief descriptions of the material science underlying their functionality, somewhat of a template or cursory roadmap to deal with climate change and the transition to circular supply chain management. Topping it all off will be a best effort to describe innovations in the field of computing with an overview of the material science behind it. Concluding with a few comments on the human condition, sort of a continuation of our co-evolution with the Technosphere. So stick around. This is Weltanschauung, the nexus between inner and outer space.
Your attention, please. At the recommendation of the International Time Bureau, commencing at 23 hours, 59 minutes, 60 seconds UTC, an extra second will be inserted into the NBS time scale. This adjustment is required to maintain internationally coordinated universal time as broadcast from these stations in close agreement with UT1 or astronomical time.
Separate. Here it comes.
Leading off the opening set of headlines devoted to universal evolution and climate change, we begin with how cosmic winds transform galactic environments, in which researchers from Ohio State University modeled how elements move across star-forming regions. They found that high-powered streams of charged particles and gases, aka galactic winds, can change the chemical makeup of the host galaxies they form in simply by blowing in a specific direction, using NASA's Chandra X-ray Observatory to observe the nearby spiral galaxy NGC 253, they found that as these galactic winds blow from one end of a galaxy to another, they alter the distribution of metals and elements like oxygen, neon, magnesium, silicon, sulfur, and iron across the disk and enrich the surrounding intergalactic space. This is important because it allows us to more deeply understand how galactic formation works in other areas of the universe. Coincidentally, there's organic chemistry occurring in deep space, which is exemplified by a study from the University of Colorado at Boulder, stipulating that a simple molecule, orthobenzene, is a prime candidate for driving gas phase organic chemistry occurring within stellar nurseries. Apparently, this ring of 6 carbon atoms and 4 hydrogen atoms can readily combine inside these cold molecular clouds, which often hover just 10 degrees above absolute zero, to form a wide range of larger organic molecules, alluding to the fact that the universe's carbon atoms forming in the hearts of dying stars then become parts of planets and even living organisms. Likewise, scientists employing NASA's Webb Space Telescope aimed at a young star system with a protoplanetary disk in the Orion Nebula speculate that the UV emissions emanating from it might actually provide the necessary source of energy for methyl cations to form, and once formed, promote additional chemical reactions to build more complex carbon molecules, which confirms the central importance of methyl cations in interstellar chemistry that plays a critical role in the early chemical stages of the origins of life. Next, researchers from Akita University demonstrated a mechanism in which carbon atoms can come together on the surface of interstellar ice grains to form diatomic molecules, which is further evidence that carbon-based chemistry can occur in the cold expanse of interstellar space, which is central to understanding the chemistry of the universe, in addition to the origin of life on Earth and the possibilities for life elsewhere. Another study revealed that the appearance of handedness or chirality of amino acids appears to have cosmic origins, as demonstrated by investigators from the University of Tsukuba. And finally, homochirality appears to emerge spontaneously in prebiotic chemical networks that adapt to optimize energy harvesting from the environment. All of which brings us closer to understanding the complex history of our own biochemistry. Getting down to earth, an ongoing barrage of studies continues to shed light on the evolution of carbon chemistry, weaving ever more intricately connected patterns into the molecular tapestry which spawned life on our planet. One prime example being a redo of Stanley Miller's famous experiment, which mimicked Earth's primordial conditions using electrical sparks to simulate lightning in a closed chamber containing methane, ammonia, water, and molecular hydrogen to produce a variety of amino acids. As it turns out, a stormy active sun may have kick-started life on Earth instead of lightning. Adjusting for what we now believe to be the correct constituents and concentrations of primitive Earth's atmospheric gases, NASA researchers validated the idea that solar superflares thought to have occurred much more frequently than today as the most likely culprit for kickstarting these chemical reactions. Not only does this account for the paradox of a dim sun, but suggests our active young sun could have catalyzed the precursors of life via solar particles more easily and perhaps earlier than previously assumed. Jumping forward to the interplay between planetary dynamics and evolution, there's mounting evidence that plate tectonics is vital for establishing and maintaining life on Earth. In fact, plate tectonics is a key reason why Earth currently has a temperate living environment and could be an important factor in the search for habitable living environments on other planets. Acting in concert with this is the mechanism of silicate weathering, a geological process by which the slow and steady weathering of silicate rocks involving chemical reactions ultimately draws carbon dioxide out of the atmosphere and into the ocean sediments, trapping the gas in rocks, a complementary role to plate tectonics in regulating the Earth's geochemical carbon cycle, a geologically constant force for keeping carbon dioxide and global temperatures in check. In other words, a stabilizing feedback, signifying that these two multi-million-year cycles are key regulators of climate. The carbon silicate cycle via the sequestration noted above, and outgassing via the aforementioned mechanism of plate tectonics from volcanoes. Life actually plays a global role in its own evolutionary process, as exemplified by the effects of land-plant evolution on Earth's chemical composition over the past 700 million years. A team from University of Southampton uncovered compelling evidence for a dramatic shift in the composition of rocks making up Earth's continents, which coincides almost precisely with the onset of land plants. Chemical characteristics of zircon crystals generated at this time indicate a significant slowing down of sediment transfer to the oceans, just as they had predicted. The researchers show that vegetation changed not only the surface of the Earth, but also the dynamics of melting in Earth's mantle. And topping off the synopsis of the ascent of biochemistry is a landmark study on the geological distribution of sediment and nutrients over the last 500 million years that showed how landscape dynamics determine the evolution of biodiversity on Earth. Known as sediment flux, researchers from the University of Sydney proposed a unified theory that connects the evolution of life in the marine and terrestrial realms to sediment pulses controlled by past landscapes. In short, movement of rivers, mountains, oceans, and sediment nutrients paced by the geological timescale of plate tectonics are the central drivers of Earth's biodiversity. These are just a few examples demonstrating the fundamental dynamics of the carbon cycle, and so the interplay between biochemistry and geochemistry under the rubric of Earth's evolutionary trajectory, which for any particular age, era, or epoch of our planet's history has settled into a homeostatic balance, aka dynamic equilibrium, and so segues into the topic of anthropogenic climate change. For starters, here's a schematic overview. The Earth has gone from this to this. So the idea that humans are forcing the current planetary dynamics for this particular epoch is based on the disruption of key biogeochemical cycles, particularly carbon. A crucial factor to bear in mind is that we're forcing things much more rapidly than the evolutionary processes previously mentioned. Since this was the overall thesis of the first episode on the Great Acceleration, the following will mostly be a list of papers highlighting how anomalies in one key cycle spill over to affect other Earth system cycles, particularly the water cycle, beginning with the finding that humans control the majority of freshwater ebb and flow on Earth, commandeering over 60% of that variability, accounted for by comparing seasonal freshwater level changes on Earth in human-managed reservoirs versus natural lakes and ponds. Next, due to rising temperatures, lakes are changing worldwide, human activities to blame. Followed by carbon emissions from dams considerably underestimated so far, researchers reevaluate the role of dams in the global carbon cycle. Additionally, another study found that hydropower dams induce widespread species extinction across Amazonian forest islands, research finds. A study from Texas A&M reveals global reservoirs are becoming emptier. Global warming is amplifying our water cycle, and it's happening much faster than we expected. Atmospheric drying will lead to lower crop yields, and shorter trees across the globe. In short, higher temps mean more evaporation. So although there may be more water in the atmosphere, the vapor pressure is stronger, resulting in a higher vapor pressure deficit derived from comparing vapor pressure versus saturation state, whereby vapor pressure deficit measures the amount of moisture the air can hold when it is saturated minus the amount of moisture in the air. When vapor pressure deficit, or VPD, is higher, the air can draw more moisture from the soil and plants. So it should come as no surprise that in all kinds of forests, there is a strong link between fire activity and vapor pressure deficit, which again is a measure of the atmosphere's thirst. This has knock-on effects on soil sensitivity to drought, which has increased significantly, thereby affecting the moisture-holding potential of soil. Flash droughts coming on faster, global study shows. And there is a shift to flash droughts as climate warms. And while we're on the topic of agriculture, it should be pointed out that humans are fundamentally altering the nitrogen cycle. Due to fertilizer runoff from farm fields, an increasing load of nitrogen is washing into rivers and streams, where nitrogen-breathing microbes break some of the fertilizer down into nitrous oxide, which is released into the atmosphere as water tumbles toward the ocean. Note that nitrous oxide is a potent greenhouse gas with 300 times the warming ability of carbon dioxide. Now moving on to the poles, investigators are finding that rising temperatures alter missing link of microbial processes, putting northern peatlands at risk. Scientists record rapid carbon loss from warming peatlands. Plant roots increase carbon emissions from permafrost soils. And finally is the little-known topic of legacy industrial contamination of the Arctic permafrost. When permafrost thaws, the Arctic could face massive problems from legacy industrial contamination and pollutants due to the instability of the melting permafrost, leading to the resulting collapse of industrial infrastructure and in turn to the increased release of pollutants from oil and gas exploration, stockpiles of mining debris, abandoned military installations, and lakes in which pollutants are intentionally poured. In short, permafrost can no longer be viewed as a solid platform for buildings and infrastructure to prevent the spread of pollutants. Winding up this tally of cyclical aberrations is a brief treatment of the degradation and probable collapse of the world's deep ocean currents. This integrated network of vertically cycling ocean currents carries heat, carbon, oxygen, and nutrients around the globe, influencing climate, sea level, and the productivity of marine ecosystems. A decline will prevent the movement of hundreds of trillions of tons of cold, salty, oxygen-rich water from reaching the depths of the ocean, and so stagnate the bottom of the oceans and generate further impacts affecting climate and marine ecosystems for centuries to come. Additionally, there are concerns regarding the distribution of ocean pH because there seems to be an interconnection between waning ocean currents, the melting of the polar ice caps, and oceanic carbon sequestration. All of the above indicating that tipping elements can destabilize each other, leading to climate domino effects, such as the interaction between the Greenland and West Antarctic ice sheets, the Atlantic overturning circulation, and the Amazon forest. So these are a few captions illustrating some of the cascading anomalies emerging throughout the biosphere. There's a lot more data which continues to accumulate. At face value, this is us on a global level, whereby sincere contemplation of this tragedy of the commons may evoke a sense of cognitive dissonance. Be that as it may, we continue with research touching on the effects of international policies and actions which indicate that globalization may be decreasing rather than increasing the security of global supply chains. Simply put, globalization allows companies to make their products almost anywhere in the world in order to keep costs down. Many mainstream economists argue this offers countries a source of competitive advantage and growth potential. However, many nations impose demands on already stressed resources in other countries in order to satisfy their own high levels of consumption. This interconnectedness also increases the amount of risk at each step of a global supply chain. Next, globalization is linked to biotic homogenization and thus the losing of biodiversity's portfolio effect. Biodiversity is changing worldwide, not only through the loss of species, but by species composition becoming more similar across different regions, a process called biotic homogenization. Just as diversification in an investment portfolio buffers it from downturns in certain sectors, diversity across ecosystems buffers natural systems from widespread collapse. The resulting loss of the portfolio effect poses greater risk of sweeping disruption by broad-scale stressors such as climate change or disease outbreaks. Followed by a brief mention of land management solutions for globalized agricultural systems, in which two leading academics warn that green farming policies may accelerate global biodiversity loss, advocating instead for land sparing as opposed to various local rewilding initiatives in developed countries. Noting that where large areas of land are taken out of farming, although beneficial to locally endangered species, this puts pressure on other areas to compensate by increasing food output. In short, this reduction in local production increases demand for food imports and so damages biodiversity overseas. By and large, the tragedy of the commons is a gray area in which public welfare is tied to dire consequences, undoubtedly influenced by a wide range of powerful lobbyists, but also ingrained into our collective psyche. With regard to climate engineering, it appears to be gaining more traction. However, overall, it's a bad idea and could make things worse, and may reinforce the inertia with which industry and political leaders have been addressing decarbonization, which is problematic if political and industry interests co-opt the stylized version for pre-existing agendas and gloss over the model's fine print. A typical example, which has been given the nod by the so-called intelligentsia, employs bioenergy with negative emissions technology or carbon capture and storage. There are increasing concerns, however, on the challenges brought to water and land resources to grow bioenergy crops, not to mention the cacophony of issues involved in storing carbon in geological reservoirs. Under further scrutiny, research has revealed that this method, officially known as BECCS, or bioenergy with carbon capture and storage, is largely constrained by sustainable irrigation. In short, BECCS's potential under sustainable water and land use scenarios is low and comes with many negative environmental impacts upon large-scale deployment. With regard to biofuels, in reality, they're far from being a climate-neutral alternative to gasoline and diesel. For example, a study showed that under current land use regulations, CO2 emission factors for biofuels might even exceed those for fossil diesel combustion due to large-scale land clearing related to growing biomass. As the lead author pointed out, if cultivation of bioenergy grasses is not strictly limited to marginal or abandoned land, food production could shift and agricultural land use expand into natural land. This would cause substantial carbon dioxide emissions due to forest clearing in regions with weak or no land regulation. These indirect effects of bioenergy use are a challenge for policymakers, as food and bioenergy markets are globally connected but beyond the control of individual national policies. Tragically, the regulatory gap in the land use sector would keep bioenergy supply cheap while pushing the energy sector to phase out fossil fuels even faster to compensate for additional emissions from land use change. This spiral in turn increases the demand for bioenergy. So before bioenergy can effectively contribute to achieving carbon neutrality, international agreements need to ensure the effective protection of forests and other natural lands. There are many other geoengineering schemes on the drawing board, some just as harebrained and potentially much more disastrous. Solar radiation management, or SRM, being a prime example. But there are a few recently proposed methods which are again combined with energy production that give one pause. In general, these are direct ocean carbon capture prototypes in the very early stages of development. Leaving it at that, this final section on climate change will cover various political and economic top-down structures and schemes, beginning with a report that identified the 10 financial actors with the most influence on the fossil fuel economy and outlines the decisive role they can play in helping decarbonize our future. This group includes investment advisors, governments, and sovereign wealth funds from around the world that collectively own 49.5% of potential emissions from the world's largest energy firms, which without their due diligence, we simply won't have what it takes to meet our emissions targets and avoid catastrophe. Next, a fifth of carbon dioxide emissions come from multinational companies' global supply chains, according to a study. It goes on to say that the flow of investment is typically from developed countries to developing ones, meaning that emissions are in effect outsourced to poorer parts of the world. In short, multinationals are transferring investments from developed to developing countries. This has the effect of reducing developed countries' emissions while placing greater emissions burden on poorer countries. At the same time, it's likely to create higher emissions overall as investment is moved to more carbon-intense regions. On a related note, multinational companies headquartered in countries with tougher environmental policies tend to locate their polluting factories in countries with more lax regulations. While countries may hope their regulations will reduce emissions of carbon dioxide and other greenhouse gases, these results show that these policies can lead to carbon leakage to other nations. Next, a study argues that renewable energy certificates, a market-based tool that certifies the bearer owns 1 megawatt hour of electricity produced from renewable energy sources, generally don't reduce emissions, and firms using them are overstating their climate mitigation claims. This scheme allows large polluting companies to purchase renewable energy certificates, aka RECs. Under these emissions accounting standards, companies can report zero emissions for every megawatt hour of consumed electricity that they match with a purchased REC. However, existing evidence shows that purchasing RECs is unlikely to increase the production of renewable energy. Following that, it appears that the European Union is actually playing a shell game with its Green Deal, which pushes carbon reduction, renewable energy, environmentally friendly transport, reforestation, and sustainable agriculture to become the first climate-neutral continent, when in reality the EU will actually be outsourcing its environmental damage, such as with high imports of agricultural products of millions of tons of cereal and meat every year, as well as hedging glitches in its alternative energy infrastructure with energy imports. In short, the Green Deal is good for a climate-neutral Europe, but bad for the planet. And wrapping up climate change in somewhat strident fashion, Many developing countries have made their nationally determined climate contributions submitted under the Paris Agreement conditional upon receiving climate finance, technology transfer, and capacity building support. However, developed countries have so far failed to deliver tech transfer to the extent promised. It so happens that most patents for low-carbon technologies are held by companies in the global north. This gives them a significant competitive advantage. A crucial player in all this is China. Although the world's second-largest economy, it's still considered a developing country by the World Trade Organization, aka WTO. As such, it's a notable exception among the list of developing countries because it has received technology transfer through foreign direct investment prompted by the lure to companies of tapping into the extensive Chinese market. So not only does considering the point of trademark solutions, but also country status reveal an apparent lapse in judgment stipulating the conditions buried within the Paris Agreement, but also that of the WTO regarding the significant advantages allotted to developing countries when compared to developed. All things considered, you can probably understand that just giving away trade secrets willy-nilly on innovative technologies in a competitive global marketplace is bad business to say the least. And so you may be wondering, how on earth could anyone be duped into agreeing to such a stupid idea? And that wraps up our climate change segment. And let me just remind you, you're tuned in to Weltanschauung, broadcasting from deep in the heart of the Petro Metro, aka Houston, Texas. I'm Mike DeLeonardis, bringing it to you. Now on to energy and material science. The inextricable synergy between the two epitomized when comparing the Stone Age with the Iron Age, both of which indicate the level of sophistication of a civilization, as well as the corresponding links with the use of resources and environmental modification. The advances in material science within the last 7 to 8 decades has been nothing short of astounding, from multi-principal alloys that blur the distinction between majority and minority populations of elements to topological materials and quantum dots designed to harness the mysterious properties of quantum phenomena. These trends in bottom-up material design probe the mechanics of the molecular and subatomic realms, be it for infrastructure or energy and computation. In terms of energy, silicon has been the accepted norm of photovoltaics since their inception, which from 2010 has seen a striking drop in cost per megawatt hour, so much so that solar cells have now reached price parity with fossil fuels. As dramatic as this drop is, there seems to be successors in the wings with potential to drop the cost of solar cells even more. So let's examine potential replacements for silicon, considered the gold standard in terms of computing and solar energy production. But even though it's quite ubiquitous, it has limitations such as the environmental impacts of mining and purification, manufacturing, and recycling. Tops on the list is calcium titanate, a relatively common mineral composite. Generally known as perovskite, it's a promising alternative to silicon, not only for next-generation photovoltaics, but also for semiconductors and LEDs. Upon realizing their photovoltaic potential in 2009, the initial prototypes had very poor efficiency and even shorter lifespans. Within the last decade, however, these devices have been the fastest progressing solar technology, whose efficiencies now rival that of silicon. Their durability has also increased, again moving closer to the benchmark of silicon, which lasts about 20 to 30 years. The consensus being that perovskites are very close to commercial viability, with significant advantages when compared to silicon. Whereas silicon is relatively heavy, stiff, and opaque, extremely thin perovskites can be made flexible and transparent. Silicon processing is expensive energy intensive, and requires temperatures close to 3,000 degrees Fahrenheit, and must be done with utmost precision in order to avoid defects within their crystal structure, which affects functionality. In contrast, perovskites are easily processed from solution close to or at room temperature. They're also much more defect tolerant and may be quite amenable to inkjet printing for mass production, with the added bonus of doing away with expensive equipment or complicated chemical setups. On the whole, they're a lot more cheaper and less energy intensive. And finally, perovskites have a tunable band gap which allows for the modification of their absorption profile. In other words, these solar materials can be tuned to respond to different wavelengths of light simply by altering their composition, which means they could be used in tandem with other materials to absorb a wider range of the solar spectrum. The two major drawbacks of perovskites, however, are that the most efficient devices contain toxic lead, and although a lot of headway has been made on this, as well as the lingering problems of stability, there's still more work to do. Organic or plastic solar cells come in at a close second to perovskites with a similar production profile, are also transparent, light, thin, flexible, and have a tunable band gap. In recent years, their power conversion efficiency has surpassed double digits, and so is another option that's closing in on silicon in terms of power generation. The stability of organic photovoltaics is also shaping up and stands on the cusp of widespread commercialization for the large-scale energy market. And briefly, a new kind of wonder material dubbed phosphorine nanoribbons has been shown by researchers to significantly improve the efficiency of a solar cell. Merely a thumbnail sketch of the next-gen photovoltaic solutions for decarbonizing global energy use. What about other methods of harvesting energy apart from wind and photovoltaics? A case in point are thermoelectric devices, which typically have only been considered for niche applications like the Mars rover. They may indeed have a lot of potential for harvesting energy. In an experiment conducted at Stanford, a module was combined with a solar cell using off-the-shelf components. This prototype was able to generate a small amount of power from the temperature gradient between the cell and the air at night. The lab's director noted the prospective viability of this approach since none of the components were specifically engineered for that purpose. When considering that heat energy radiating from Earth's surface is on the same order of magnitude as solar energy reaching it, this as of yet untapped source of infrared radiation is huge. As such, there's a lot of focus on sustainable thermal energy capture, storage, and use, be it industrial waste heat from power plants, factories, and even cars, which could amount to enormous energy savings considering that estimates of 65 to 70% of all energy generated in the world is wasted as heat. Lots of ingenious solutions are being looked at, from retooling metal slag to tweaking very tiny antennas called optical rectennas for turning electromagnetic waves into direct current electricity. Even attempting to use piezoelectric materials for large-scale energy harvesting, like in prototypes being tested for non-turbine wind energy, as well as exploring the potential of a thematically similar variation known as flexoelectrics. Initial evaluations are also exploring the potential of combining these with biomaterials for harvesting energy from relative changes in humidity as well as evaporation. Before moving on to storage, an interesting caveat bears mention. Over the last few years, researchers from the University of Arkansas accomplished something that was considered impossible by capturing the thermal motion of graphene and converting it into electrical current, refuting physicist Richard Feynman's assertion that Brownian motion, or the thermal motion of atoms, cannot do work. opening up the possibility that an energy harvesting circuit based on graphene could be incorporated into a chip to provide clean, limitless, low-voltage power for small devices or sensors. With that in mind, the fact that energy cannot be created or destroyed poses some interesting questions to ponder. The bottom line is that energy is everywhere, and extrapolating climate change to its most fundamental level reveals a problem of kinetics. Within the bounds of this perspective, one could argue that humans have altered the planetary balance between kinetic and potential energy in favor of the former. Using this premise poses the question: could the choice of what sort of energy to draw from actually play a role in remediation? One of those interesting questions. Concerning the question of storage, this has and continues to be the Achilles heel of alternative energy. It's the missing link in terms of decarbonization of our energy infrastructure, because storage and portability are the practical advantages that maintain the utility and convenience of fossil fuels. In other words, coal, oil, and gas are energy dense and portable. That is, they can be easily stored, transported, and used anywhere quickly and cheaply on a large scale. Grid-scale battery storage is coming online, certainly a convenient drop-in solution that compensates for curtailment and supplies the grid when wind and solar production are down. But there are other issues apart from the supply chain, such as lifespan, overheating, and the like. Additionally, current regulatory guidelines regarding placement have overlooked the shifty practice of coupling these systems to fossil fuel plants. The increased demand for mined and processed rare earth metals also needs to be accounted for. That said, it's a prelude to enhancing the capacity to store energy captured from solar, heat, wind, etc., to use when and where it's needed at sufficient enough scales safely, cheaply, and reliably. But only time will tell their viability. On the whole, the roadmap toward complete parity with fossil fuels lies in developing materials capable of quickly storing enough energy in as small amount of space as possible, otherwise referred to as portability and energy density. Batteries have been the mainstays of chemical storage for some time, and research and development appears to be trending towards options other than lithium ions, as well as reducing reliance on scarce metals for electrodes, in addition to reducing charging time and increasing durability. That said, fuel cells may have more potential in terms of upending the monopoly that fossil fuels hold on portability. The ultimate goal is to design materials that are capable of storing the most amount of energy in the least amount of space that's quick and easy to load in and get out. This may be the key advantage that fuel cells have over batteries. In this respect, metal organic frameworks and their successors have generated a lot of interest because they have many applications, such as catalysis, sensing, and gas storage. Abbreviated as MOFs, these are nanoporous and flexible crystalline structures with a modular arrangement of metal ions and molecules, aka organic linkers, developed for absorption of small molecules such as gases, and can be modified to have specific chemical and physical properties by using different metals and organic linkers. These are essentially molecular scaffolds designed to have as much internal surface area as possible for capturing and storing or filtering as much of whatever is loaded into it. In fact, it's been estimated that a pile of MOF material the size of a pea has an internal surface area about the size of a football field, which obviously holds great promise in terms of energy storage and portability. There's actually been success with loading MOFs with light-absorbent molecules that act like photo switches in which solar energy has been stored for months and retrieved afterward. The combination of tunability and immense surface area of these materials holds great promise for hydrogen storage, and so has garnered considerable interest for advancing the efficiency and performance of hydrogen fuel cells. A display of their versatility was revealed in the spring of 2023 when researchers simultaneously purified herbicide-tainted water while also producing hydrogen. From energy storage to environmental remediation, even to the advancement of semiconductors, MOFs and their counterparts are predicted to be the defining material of the 21st century. With regard to hydrogen storage, there are a lot of options on the drawing board. It's a highly explosive, very light gas that takes up a lot of space, which is why MOFs are so appealing, because these solid-state materials are theoretically able to store an immense amount of hydrogen in a much smaller space and do it in a non-volatile fashion at ambient temperature. On top of that, MOFs can be packed into chambers with all sorts of shapes and sizes, which is great for cars and trucks, whereas conventional means of hydrogen storage entails very thick and bulky high-pressure tanks for gas or extremely cold temperatures for liquid, which is expensive as well as an engineering nightmare. Metal hydrides is another option for hydrogen storage with some niche applications, but adds a lot more weight per unit volume. In addition, an ammonia-based solution is also being examined, which appears promising not only due to the fact that an extensive ammonia delivery system already exists, but it's also portable at standard temperatures and pressures. And ironically, it's more energy dense than liquid hydrogen near ambient conditions. There's even been discussion of using baking soda as a storage medium, but for now it's merely an academic curiosity and we'll leave it at that. With regard to ammonia synthesis, there's been a few claims of success in testing zero-carbon methods of production. Quite relevant because the standard method, the Haber-Bosch process, is extremely carbon intensive, and these new ways of making hydrogen and ammonia don't require massive infrastructures, which translates into flexible scalability, even on-site generation. In essence, these two systems are synergistic, which means this interplay between hydrogen and ammonia is actually an artificial cycle, the essential trademark for creating circular supply chains. Once considered a mere curiosity, research into artificial photosynthesis is also starting to produce results. Technically known as photocatalysis, it's basically harnessing sunlight to drive chemical reactions, and is a hot topic of research exemplified by the myriad of studies on the topic, many combining water treatment with hydrogen production, which was briefly touched on a minute ago. Work by a team at the University of Cambridge has made quite a bit of headway in this area using their artificial leaf, a floating solar-powered device to turn contaminated water or seawater into clean hydrogen fuel and purified water, addressing both the energy and water crises. In previous experiments, they've also been able to convert carbon dioxide and water into liquid fuels that can be directly added to a car's engine as drop-in fuel. Moreover, they were able to convert captured CO2 and plastic waste into sustainable fuels and other valuable chemical products. These are some examples of using waste streams not only to make clean energy, but also to produce useful products. So that's a brief look at photocatalysis. Before leaving the topic of energy, let's take a look at radiative cooling, which plays a significant role in regulating climate in terms of polar and glacial ice, as well as clouds, because it pertains to albedo or reflectivity, which is rapidly decreasing worldwide due to the loss of global ice cover. Furthermore, it's the principle behind potentially disastrous solar radiation management schemes. An important distinction applies here, though. The following will cover material-based solutions intended to be incorporated in our buildings, vehicles, and possibly even roads. In other words, it's an infrastructural approach at ground level. whereas radiative cooling via solar radiation management is outright geoengineering intended to manipulate the atmosphere, an intervention that not only requires constant vigilance, but also comes with the potential for systemically negative repercussions. The approaches to develop materials that remain cooler than their surroundings with the added ability to reflect the sun's rays back in outer space, aka radiative cooling. A team at Purdue University did just that by creating an ultra-white paint that pushed the limits on how white paint can be. The formulation reflects up to 98% of sunlight, which also means that the paint is the coolest on record. The researchers demonstrated that the paint can keep surfaces 19 degrees Fahrenheit cooler than their ambient surroundings outdoors at night. It can also cool surfaces 8 degrees Fahrenheit below their surroundings under strong sunlight during noon hours, whereas typical commercial white paints get warmer rather than cooler. Paints on the market that are designed to reject heat reflect only 80 to 90% of sunlight and can't make surfaces cooler than their surroundings. Purdue's white paint is the result of 6 years of research building on attempts going back to the 1970s to develop radiative cooling paint as a feasible alternative to traditional air conditioners. The overall mechanism employed to achieve the highest refractive index or light scattering ability begins at the nanoscopic level, hinging on molecular shape and type. They've come up with at least 2 formulations for this paint, one for buildings and one for vehicles, both with the potential to drastically reduce the reliance on air conditioning and so conserve energy. In another paper, a joint team from Korea developed a transparent radiative cooler that could transmit visible light, reflect near-infrared light, and emit mid-infrared rays, exhibiting both transparency and radiative cooling by selectively reflecting near-infrared light, which was confirmed by an outdoor rooftop experiment in which this cooler reduced the inner temperature of an absorbing system 14 degrees C and its own temperature, even when combined with commercially available paints. So it appears that radiative cooling technologies such as these not only have the potential to decrease the temperature of our infrastructure and so the energy we use to cool, but may also act as a mechanism to reflect much of the sun's rays back out into space and so cool the surroundings at scale. These snippets are but a sampling of how material science might upend how we get, store, and use energy in the future, hopefully sooner rather than later because time is running out. The big issues here are catalysis, energy density, storage and portability, on-site generation or ease of production, and ease of use, and finally, minimal effect on the environment. Bring it all together, and the advantages over fossil fuels are obvious. With respect to catalysis, it's the engine that drives the chemistry that makes this stuff work, and the trend is moving away from precious and rare earth metals towards stable organic catalysts. The gold standard consisting of single atoms of common metals trapped inside carbon cages called porphyrins. Another plus in terms of less mining and so less environmental impact. An interesting twist is that many of these technologies leverage the principle of chirality, such as with the manipulation of ion attraction and even the flow of light, designing from the bottom up at the molecular and subatomic levels, revealing a trend towards improved mimicry of natural systems. But if we actually achieve the capacity of on-site energy generation and make it portable with minimal infrastructure, the most likely outcome would be creative destruction. In other words, the widespread adoption of these nascent technologies would subvert many of the centralized infrastructures we now depend on, such as the grid, which would overturn the systems and economics across energy sectors worldwide, from extraction to distribution, for these are truly disruptive technologies. A plus, however, is that these new Alt-E schemes would negate the requirement for energy imports and thus the leverage that politically volatile countries use to affect global politics and trade. Regarding the amount of energy it takes to maintain the bedrock of our information infrastructure, estimates of as high as 10% of the world's electricity consumption is used by the information and communication technology sector, aka ITC, which is expected to more than double by 2030. One way of reducing that is to change how digital computers use electrons to calculate and store data, which currently work by directing electron flow and storing charge. The idea is to replace direct current and voltage by manipulating a magnetic property of electrons referred to as spin. The key is aligning the spin of relatively stationary electrons in order to direct it through an integrated circuit. Simply put, the power to manipulate spin in such a way allows for the creation of logic gates and conducting pathways to transmit spin current and stored in active memory. But instead of directing the flow of negatively charged electrons, it'll be the flow of spin. The concept of using electron spin as bits instead of voltage requires much less power and so generates much less heat. An added bonus is that unlike charge, electron spin remains stable when the power is shut down, meaning that the contents in random access memory would still be intact, even when the power is off. Enter the term Spintronics, supposedly inspired by the evolution of magnetic recording, from 8-tracks, cassettes, and FAT32 hard drives. Many labs around the world are investigating the possibility of using electron spin to store, process, and transfer information with the ultimate goal of making faster, more efficient computers that use a lot less power. In theory, the tiny capacitors in RAM will be replaced by components that'll be able to store spin instead of charge, giving rise to faster, more efficient computing done with spin current instead of the flow of electrons. A whole new way of manipulating the properties of electrons to perform the standard digital computing we have relied on for the past 7 or 8 decades. This also has the potential to move beyond the limits of Moore's law, which current integrated circuits have just about maxed. Quite complicated but compelling stuff that delves deeper into quantum phenomena ingrained in the elemental and topological properties of materials. These are the quantum boundaries being pushed by material scientists across the world. Today's standard computer architecture is another hurdle in terms of miniaturization of digital circuits. As circuits have shrunk and become more powerful, the inherently bad trade-off was more heat generation, one more impediment to extending the longevity of Moore's law. Enter the phrase von Neumann bottleneck, an innate derivative of the architecture bearing the same name, which has been the standard design of integrated circuits since their inception. The basic gist of this architecture is that the partition of the processing units performing the actual computation from the memory units storing the data results in a bottleneck or traffic jam between the two. Therefore, this architecture limits data flow to a sequential or serial process. That is, only one piece of data can be handled at a time, and in between is a lot of fetching, decoding, and executing for each piece of data, which creates a bottleneck or traffic jam between memory and the CPU. So this systemic flaw of von Neumann architecture is inefficient because it takes a lot of time and costs a lot of energy, barely noticeable in real time because of the speed at which electron flow occurs, but significantly adds up when considering the whole. And although the aim of combining memory and logic or in-memory computing has been around for quite a while, it's simply not feasible with standard digital electronics because compared to von Neumann architecture, it would take up much more space to build separate arithmetic, logic, and processing units for each memory register, and so is not practical. So all in all, von Neumann architecture served its purpose, which is still the standard today. The current state-of-the-art merely sticks multiples of such units in a single IC that's marketed as parallel processing. Coincidentally, however, a eureka moment occurred about a decade and a half ago that appears to have shattered the barriers to realizing true in-memory computing when a compelling theory was realized that shook the foundations of electronics. It so happens that three basic concepts of standard electronics, namely resistance, capacitance, and inductance, have complementary phenomena. Their respective counterparts aptly named memresistance, memcapacitance, and meminductance, the latter of which was confirmed only a year ago by a team at Texas A&M University, and so called because their current and voltage properties are dependent on previous values of current or voltage. This is a key point to realizing in-memory computing. This new insight has inspired those in the field to develop practical methods of using these recently discovered phenomena to usher in new ways of performing computer logic at the actual level of the hardware. A lot of progress has been made with memresistance, the first of the mem counterparts discovered about 15 years ago, and appears to be following a similar trend in material design for alternate forms of energy and storage by combining organic molecules with common metals, which is showing some surprising results. For example, a couple of years ago, another team at Texas A&M University designed a metal organic molecule that was a quantum leap above the original metal oxide memristors, which could only switch from metal to insulator at just one fixed voltage. Because their new organic molecular device could switch back and forth from insulator to conductor at several discrete sequential voltages. Testing showed that their devices could perform fairly complex computations in a single time step and then be reprogrammed to perform another task in the next instant, demonstrating that only one of their molecular devices with its different decision trees could perform the same computational functions what would take thousands of conventional transistors to do, offering a significant boost to the longevity of Moore's law. The beauty of memristors is that they can be reconfigured on the fly for different computational tasks by simply changing applied voltages, a hallmark quite reminiscent of brain plasticity, which makes memristors major game changers in the field because these devices change resistance depending on a memory of the past current. Hence the name memory resistor or memristor. And it's this peculiar behavior that's surprisingly similar to that of neural synapses. So the memristor has become the essence of neuromorphic architectures, the heir apparent to von Neumann architecture. Hence the name neuromorphic computing. Much like neurons, which are responsible for data storage and processing in the brain, scientists want to combine storage and processing in a single electronic component, the memristor. And teams the world over are doing just that, including designing optical or light-based memristors, which could play a major role in revolutionizing high-bandwidth neuromorphic computing, machine learning hardware, and artificial intelligence in the optical domain. So using light to revolutionize computing is another emerging field of designing photonic integrated circuits, which segues into quantum computing because a number of methods seem to be coalescing toward photonic or light-based computing. To review, standard digital computers serially tabulate bits of either 1 or 0, an additive process based in absolute terms, which is great when the data you have is complete and concrete. But reality is often chaotic and unpredictable, requiring the ability to assimilate, assess, and react to unpredictable situations quickly. Traits innate to all life forms with developed nervous systems. Simply put, it's the ability to learn on the fly, even with a limited amount of data. This is the gray area that AI, or artificial intelligence, is trying to tackle. And so far, although the spectacular imagery, sounds, and music may be impressive, it's merely mimicry that falls short of the actual intuitive processes that come automatic to us. Namely, what we often think and do with little consideration requires gobs of programming and computer power for standard computers to accomplish, if at all. Enter the world of probabilistic and quantum computing, new forms of computation that evolved out of much of the aforementioned research on these strange topological materials extending into the quantum realm. Probabilistic computing might best be described as a parallel method that's based on probabilistic bits, aka p-bits, which interact with other p-bits in the same system and fluctuate between positions as opposed to being either 1 or 0. These computers are geared toward finding optimization or decision-making problems based on likelihood that are difficult for classical computers by means that are much faster. In short, they find the most probable outcome among a number of variables, which is primarily done through harmonizing or settling into the most likely energetic state. So it's quite reasonable to conclude that this scheme of computation is derived from the laws of classical and statistical thermodynamics. The bottom line is that in probabilistic computing, bits interact with one another and fluctuate between 1 and 0 as opposed to being one or the other, which resembles an analog approach. And at the moment, it appears that probabilistic computing will be a more feasible way to find those solutions that are out of reach of binary computing. This may offer a window into more detailed mechanisms of truly complex systems, from molecular dynamics or market fluctuations to variabilities in climate or weather, and at present appears to be closer to reality than quantum computing, primarily because of the sensitivity of entangled quantum bits to environmental factors. The integral methods of these schemes are quite different than the standard forms of computing we're used to and are somewhat viewed as sort of complementary, with quantum computing considered the holy grail, because quantum computing's basic operation relies on the superposition of various quantum states of particles such as spin, frequency, polarization, and/or topology, which are then entangled during the process of computation. Superposition refers to the existence of various states of a quantum bit or qubit at the same time. So with respect to calculation, this is like having both a value of 1 and 0 simultaneously, encoded from the state of an electron or nucleus of an atom, or the polarization of a photon, for instance, which would provide a solution when probed, aka observed. The main advantage of quantum computing over classical is that superposition of qubits acts like a supercharged shortcut in the computation process, which offers exponential increases in the speed of computation many orders of magnitude over classical computing. And what's really cool is the potential of combining multiple states of superposition like spin, polarization, and/or topology, for example, which jacks up the computing capabilities exponentially for each new state added. These superimposed qubits are then entangled so that the bits interact with one another, whereby the state of each qubit is coherent or joined up with all the others. This is the key reason why the theoretical power of quantum computers could eclipse today's most powerful supercomputers, as they've eclipsed the simple abacus, to use an analogy. So what may take thousands of years for today's best supercomputers to solve would theoretically take a quantum computer only a few minutes. Entanglement arises from the intimate connection between particles and can occur regardless of the physical distance between them, which is why it's often referred to as spooky action at a distance, as Einstein famously noted. A quite perplexing phenomenon that opens up the potential to expand from quantum computing to a future quantum internet, using superposition and entanglement as a means of foolproof encryption. This is the bleeding edge of information technology, quite rudimentary at this point, and although there appears to be some working prototypes, time will tell if the promises of these techniques will come to fruition. That said, there is little doubt that research in this field will further our understanding of quantum mechanics. The important point to all this is that the substrate of all these fascinating technological achievements is the material sciences. And this quantum revolution born out from these material advances extends beyond the realm of computation to include sensing, imaging, as well as energy, to name a few. Carbon-based materials like graphene are coming into their own, gradually replacing silicon in many hardware applications while complementing it in others. Ironically, the convergence of these two elements was essential to the evolution of life on our planet as vital ingredients for the biogeochemical cycling of carbon. By chance, it so happens that bioengineering is playing an ever greater role in the material sciences, starting at the nanoscopic level where porphyrin cages shape charge around metal ions, to graphene doping and quantum dots, to artificial neurons and DNA scaffolding of integrated circuits, using genetic engineering to build microbial circuits, to developing organoid intelligence, even artificial brains which learn like a biological brain does. Computing for enumerating standard bits and bytes, morphing from directed flow of electrons to directed flow of electron spin. Honest-to-goodness in-memory parallel computing, and new paradigms based on integrating chemical gradients, energy, and quantum fluctuations by exploiting the properties inherent to discrete subatomic particles. These revolutions in computation coincide with new methods of maximizing memory storage that appear to be trending toward using genetic material, concomitant proclamations indicating feasibility within a decade or two, the need of which is also quite pressing in terms of space as well as energy. These are the links between energy and computation borne out by the material sciences, both paralleling one another in terms of collection and portability, and both trending toward more integration of carbon-based molecules into their material design, somewhat ironic because of carbon's fundamental role as the scaffold of life. So maybe in the grand scheme of things, materials have always been one of the great disruptors in the evolutionary process, progressing toward us and out from us, wherefore materials are at the center of applied and basic science, quite reminiscent of the Manhattan Project, a moment when a collection of some of the greatest minds in history came together in a fever pitch to produce the first atom bomb. Evidence that the Second World War was a pivotal moment in the ascent of the modern scientific industrial complex. From the construction of the A-bomb to the genius of Alan Turing in breaking the Enigma code, whose endeavors were hailed by John von Neumann as central to the concept of modern computing, from Aristotle to Francis Bacon up to the present, where governments and entrepreneurs rush to get the industrial, military, and technological edge through investments in businesses, science schools, universities, and research institutions. A testament that science is bound up with economic and technological hegemony, as well as a testament to the evolution of the human condition, a conundrum spinning into the future. Since before the dawn of civilization to the present, with each advance our capabilities extending further outward, gaining on the world around us. Yet these successes lacking any broad perspective on the boundaries overcome in the process. Something gained and something lost. So here we are now, the most recent of a progressive iteration, the Technosphere. From the perspective of recorded history, its ascent spans the course of human activity before the advent of agriculture. But in terms of the age of our world, something that appeared in the twinkling of an eye to become a major force in terms of planetary dynamics. A new entity powered by a global economy rooted in consumerism. And attainment within this sphere is the standard by which we measure the world and our status within it. Our preoccupations predicated solely in economic terms or the ability to buy goods and services, indicative of the artificial bounds constraining our collective field of view and so directing our priorities. Myopic to the boundaries and limits set by nature, so that we barely even consider the raw materials extracted and fed into the supply chains that fuel this economic engine. This is us, and this is the Technosphere, and its progression eerily exponential. This is now, and now is the great acceleration, peaking in a momentum which has forced the planet into a new geological epoch. And this new sphere is the civilization we made. All we know filtered through a lens which changes as our commodities change, and so we change. Over 60 years ago, archetype agencies were developed in the U.S. to fund high-risk, high-reward research, providing greater freedom to take on highly ambitious technical challenges with the aim of fostering major breakthroughs. From this came the internet, presaging the explosion of social media and mobile tech, emanating with its own superposition in terms of its effects. Its effects on the current social milieu most poignantly demonstrated with respect to agency, enhancing the ability to shape one's own choices and actions in the world of today. The initial promise of the information age was the potential for all to be informed and communicate like nothing before. But the flip side was a narrowing of our focus to a world on a screen, anywhere just a click away. The irony is that this increased focus blurs out the periphery, the shadow side of delving deeper, while at the same time exposing the sum total of our collective conscious on display. A hindsight glance on the dreams of unveiling more objective truths has revealed a grossly overlooked catch-22, which are the innumerable ways for anyone to spin and promote narratives with no basis in reality. And so an ideal of rational connection was quickly overwhelmed by an escalating amount of BS and social discord, especially stoking age-old divisions. A new medium where anyone is enabled to get away with pushing defunct predispositions via newfangled narratives, spiking toward hate-filled rhetoric, splintering into groups anchored to centrism. This is the overlay of the global group mind imprinted on the internet, expressed through social media, metastasizing into every means of discourse. Now manifest as a coagulated patchwork of obstreperous egocentric rants, forcing nouveau lingo with unconditional demands for codification, injecting this whiny-weeny hypersensitivity into the literal exchange to such an extent that even the canon of science itself is at risk of being undermined. Morals equated with fixations on victimhood, leveraging an agency into itself, and history square-pegged into false narratives steeped in identity, opening the door to genocidal hatreds and conflicts. Claims of progressive ideals merely capitulation to a militant base fixated on persecutory ideation and political affiliation. Civil rights twisted into favoritism for voters in exchange for widening their base. Individual identity couched in solidarity through the lens of victimhood. The concurrent infiltration of academia backwashing into traditional media by political, ideological, and racial activism, amplifying this mayhem into a veritable spin junkie free-for-all. Paving the way for deconstruction of objective scientific facts, reason, and inquiry, and replacing it with mere consensus being funneled through the political arena. Be it statistical trickery downplaying climate change, or psychobabble extolling the fundamental transformation of gender based on whimsy and consumer cosmesis, political and corporate toadies sidelining facts to fit their agenda, fueling this polarized firestorm. The voracious sensationalization, codification, and institutionalization of this pity party, enabling blamers and reparationists, sidelining standardized vetting and replacing it with diversity, equity, and inclusion, sowing greater division by flipping facts and overblowing narratives into draconian worldviews, undermining the basic premise upon which the free world was built, undercut by a narcissistic group mind couched in identity. And activism merely a vehicle for attention, agitation, virtue signaling, and focusing ancient hatreds magnified through the lens of traditional media. From its inception, social media became the de facto means of identity projection, a medium of spin more akin to a proving ground for hyperbole, half-truths, and outright lies sold as facts, the contemporary opiate of the masses, bleeding out into the entire apparatus of global mimetics, and it has become unwieldy, particularly in democratic societies that are now bowing under the strain of sinister ad hoc ideologies and agendas promoted by narcissistic ideologues, extremism couched in euphemisms, and suffrage used as proxies for power grabs, taxing the ability to maintain the integrity of free speech. Political contests waged primarily through personality and identity, sidelining policy, enabled by traditional mass media elitists running the gamut from entertainment to so-called major news outlets. Corroborating data suggests that higher narcissism may be linked with more political participation, linking higher levels of narcissism with behaviors that could be harmful to functioning democracies, politicians shifting focus from civic responsibility toward one's own self-interest and gratification. Higher narcissism in the general public linked to more conflict and civic strife, in addition to less cooperation, compromise, and forgiveness. A war of ideas where ideologies rail against rational conclusions and standards, the uncanny parallel of this with the post-World War expansion of products into the marketplace derivative of the scientific-industrial complex is hard to ignore. The hemorrhagic abundance spawned via the Technosphere extolled for providing new wonders and conveniences, undoubtedly true, but also translates into the entitled existence that we all expect. A great seduction stoking a pressured existence, eclipsing any specter of cognitive dissonance to counterbalance the subtle allure of the madman, beckoning the masses toward more greed and hubris, with those on the fringes forced into debt. As such, the limbic nature of consumerism is the key focal point in the backlash against the very framework that begat it. The ultimate consumer vehicles of social media and mobile tech portraying the id. Interestingly enough, research on consumer behavior suggests that an initial choice is followed by a preference. a gut reaction spanning from early infancy up to and through adulthood. In short, we like things because we choose them, and we dislike things we don't choose. And through the constant bombardment of advertising and media, we are always forced to choose. Out of this, the information age is forging new systems of power, emanating from the click of a button, shaping how we move through the world. So initial choices may not be explicitly based on merit, but emotionally driven. This particular finding strikes at the heart of social media and polarization, quite simply an addictive medium, another fix for that dopamine rush. The dark side of mobile tech and social media magnifying the tapestry of relativism gone amok, a stringent hardening the edges of polarization, forcing the social, political, and economic structure of the free world. When viewed through a wide-angle lens, it appears that the implementation of many of the objective and humanist ideals spanning from the ancient Greeks to the Enlightenment mutated and metastasized. The ideals of equality, liberty, skepticism, and revolution turning back on itself, so that now anal extractions prevail over established objective evidence in an atmosphere of anything goes, in a pitched battle between the ideas of the Enlightenment versus the relativistic ideologies of postmodernism, aka facts versus feelings, whereby the preceding gave birth to the latter through the rubric of tolerance and the spread of consumerism borne out by the Industrial Revolution. A visceral dogfight on all fronts, taking precedence over objective reporting and reasoned debate. The parallels of the destruction of Holocene norms versus the destruction of Enlightenment norms seems to be the product of how the shadow manifests itself, for good or ill, within the macrocosm of the human experience. An evolution bound up with its origin. Just as the Holocene is largely credited for providing the springboard of civilization, the values of the Enlightenment have generated the social, political, economic, and scientific standards that built the structure of the civilized world. Both seem to be imploding, another strange twist of parallels within the elaborate interplay of duality, whereby the initial ideal of unity, originally touted as an inevitable byproduct of the internet, spat out a balkanized casing of bubble wrap instead. Visceral versus cerebral, which in the grand scheme of an evolutionary context is another perspective of how duality plays itself out within the whole. Evidence suggests that even our brains were always bound up with our guts. Notably, a study indicates that synaptic evolution is linked to the interplay of the digestive mechanics of brainless sea sponges with its microbial milieu. Not to mention the multitude of studies exploring the effects of the gut microbiome on the brain, known as the gut-brain axis. So does the stomach imply the brain, or the brain imply the stomach? This is now, and it's a product of who we are and what we make. So one may ask, what does this foreshadow? As we see the degradation of the physical norms of the previous epoch, so we see the degradations of the norms implied by the Enlightenment, the standards that laid the foundation of modern civilization. This is the great acceleration, an interesting convergence of mind and matter. And the world turns, inside out and outside in. So what of the future? Only time will tell. And so it goes. You have been tuned in to Weltanschauung, broadcasting from deep in the heart of the Petro Metro, aka Houston, Texas. I'm Mike DeLeonardis, and I have been bringing it to you. See you on the flip side.
I guess I just don't know. And I guess that I just don't know. makes me go. That I'd sail the darkened seas on a great big clipper ship, going from this land here to that on a sailor's suit and cap. Away from the big city where a man cannot be free of this town and of himself and looks around. Oh, and I guess that I just don't know. Oh, and I guess that I just don't know. Heroin be the death of me. It's my wife and it's my life because a man